In C and other structured languages, one strategy for planning what we're going to build is called top-down, which means that we start with the big thing and we build it by building the parts it's made of. To do that, we need a coding structure called functions, which are essentially named blocks of code. In this video, and the one that follows it, we'll see how we think about what we need to build, and then how we design the functions we need to build it. As a general rule, we can follow these steps to figure out what we need to build. First, we need a clear problem statement. We need to understand the problem well before we can figure out how to build the solution. Then, we list the data we'll be working with. Inputs are things that someone or something else is giving us. Maybe a user enters some information, or we get it from other systems or other parts of our system. There may also be relevant data that we need to manage. And then the last data we need to think about are the results our program should compute. Once we understand the data, we write out a strategy for solving the problem in English, and we keep refining that strategy until it maps directly to code, and then we test to be sure that our code actually works. Now, I like these 5 steps well enough, and they are what people will say for how you go about doing top-down design. However, if you really did that for the whole program, you'd have a lot of code before you could test anything. When we're trying to debug something, the more untested code we have, the harder it will be to find where the problem is. Therefore, we really want to do these 5 steps on much smaller pieces of the system. Make sure that each one of those little pieces works by testing it, and then put them together to build the big solution. Here's an example problem that we can play with. The goal is to output this graph that's a section of the sine curve. Now, if you don't know what the sine curve is, don't worry. It's a trigonometric function that takes any real number and converts it to something between -1 and 1. When they're all graphed together, they make a pretty curve. Because we're doing this with ASCII graphics, we have to be able to output it with print statements. So we're going to turn the graph vertically. The x-axis is vertical instead of horizontal. Here's our problem statement. Our inputs are where we want the graph to start and stop, the range of degrees that we should build the graph for. Our relevant data is the width that we want the graph to have. Our output is the graph, and here's my strategy. I'm going to build a loop that walks through a range of numbers that we've been given and outputs a line for each one. One way that we can visualize our top-down design is a technique called structure charts. In this diagram, the top box represents the entire program. In our case, we want to build a graph printer. In order to do that, we're going to need to build 2 things, something that prints the heading and something that prints the graph. Printing the heading is pretty trivial, so I'm not going to describe it in pieces. However, printing the graph still seems hard, so I'm going to describe the pieces I need to do that. I need to be able to compute how many spaces over an asterisk needs to go, and then, given that number, I need to be able to print one line of the graph. So you can see that the name of the process top-down design comes from the idea that we start at the top with the whole program, and then we work down, giving details of what we'll have to build. When a box has a layer below it, like print the graph, we're essentially saying that when we build the code for printing the graph, the code will use the boxes below it. In C, a function is a named block of code. The structure diagram of our design maps to our code in that each box becomes a function. The box at the top is our main function. The rest of the boxes are also functions. When we build them from the bottom up, testing each one before we use it to build the one above it. The last thing that gets fully built is the main function at the top. So, top-down design leads to bottom-up implementation. Let's walk through how that would play out for our graph printer, and along the way, we'll learn about declaring functions, passing information into functions, and getting information back out from a function. The first thing this structure chart tells me to build is a function that prints the heading. We can use the 5 steps of top-down design for each function. For this one, The problem we're solving is that we need to print out the heading of our graph. We have no inputs, but we need to know the width of the graph. The output is the heading with the scale spaced appropriately for the width of the graph. Given that data, this is my strategy. There are 3 lines. Outputting the first is trivial. The second depends on the width of the graph, so I need to use loops to space out the parts of the axis legend. The third line also depends on the width of the graph, so I'll use a loop there too. This is the code that would result from that specification. If loops are unfamiliar, don't worry. We'll talk about them in a video soon. The point isn't really what the details of the code are. The point is that our main function is being built a little bit at a time. Here, it's calling our print heading function. When we want to execute a function, we put the name of the function followed by parentheses. That will make the computer jump to the print heading code, run it, and when it's finished, jump back to the main to finish running. I think we need to look more carefully at exactly what happens when you call a function in order to begin to see how the machine really works. When we call a function, we need to remember where it should go back to when the function exits, and we need to make space for local variables that the function uses. We're going to do that with a structure called the call stack. In the call stack, there is one entry for each function that we are currently working on. We call those entries stack frames. Among other things, the stack frame holds all of the local variables for that function. We use the word stack here, just like a stack of dishes. When we call a function, a new stack frame goes on the top of the stack, and when we exit, the entry at the top of the stack gets deleted. Let's think about that in the context of our graph printing example. When we run a program, that has the effect of calling the main function. That makes a stack frame for that function call. There are 2 registers in the system that help us keep track of the stack. The stack pointer always points at the top of the stack, and the base pointer always points at the bottom of the current stack frame. The first thing our main function does is to call print heading. When we jump to that code, we create a new stack frame on the top of the stack. Notice that both the stack pointer and the base pointer move so that they now surround the new stack frame. When print heading exits, that stack frame will get deleted, and the stack pointer and the base pointer will be moved back to the surrounding the main frame. When the main finishes, the program has completed its run, and the last stack frame is no longer needed. At this point, we can run our code and see that print heading works. So we've built print heading and tested it by using it in the main function and watching it run correctly. One part of our program is coded and tested. Notice that there's a difference between something being coded and being complete. Nothing is complete until you can demonstrate that it works. I can't tell you how often I hear people say, "I'm 90% finished with this project," when they haven't made anything actually run. No matter how trivial a function seems, you can't be sure it works until it runs, and you can verify in some way that it did what it was supposed to do. So I don't mark anything off the structure chart until I've demonstrated that it works. To see the rest of this graph printer get built, and to learn how to pass information into and out of a function, please watch part 2 of this project.